Now we are going to talk about the weak law of large numbers. And the weak law of large numbers seems to have a very, very complicated statement, but actually what it says is not very hard to understand. Okay, so we are starting with the limit theorems now. And the weak law of large numbers says that x1, x2, x3, so we have a sequence of independent and identically distributed random variables, each having a finite mean expected value of xi is equal to mu, and their variance are equal to sigma square. So these random variables are different from each other, but they are identical and independent. So they are independent from each other. They do not have any correlation in between them. And they are identical, which means their distributions are the same. They are coming from the same distribution, but we do not know that distribution. What we know is about this distribution, the expected value of these random variables is equal to mu, and the variance is equal to sigma square. Once again, I'm warning you, my friends, here in this statement, nobody is talking about normal random variables. I am just using mu and sigma square for notational purposes, okay? So they are just symbolic, just to summarize that expected value of x and variance value of x with a Greek letter notation, mu and sigma square. So we do not know the distribution of x1, x2, and x3. What we know about them is that they are identical and independent, and their expected values and the variances are known as mu and sigma square. Now, then the weak law of large numbers states that for any epsilon that is greater than 0, which means you can choose any epsilon as long as it is positive. I mean, you can make this epsilon value very, very close to 0 as well. I mean, you can choose the smallest possible epsilon you can imagine, okay? I mean, you can write 0.000000000, many zeros, and then you can write a 1, okay? You can choose the smallest possible epsilon. It doesn't matter. As long as it is greater than 0, it is okay. For any epsilon, it says, okay, the probability of the absolute value of the average of these random variables in the sequence. So this is the average formulation, right? From 1 to n, I am taking the first n of these random variables to the average. The absolute value of the average minus the expected value of these random variables to be greater than or equal to epsilon is going to converge to 0 if you increase the number of random variables in that average. Okay, so let's just say this is an infinite sequence, and if you increase the number of random variables that you take into the account in the average to the infinity, if this n goes to infinity, if you take the average of more and more random variables from that sequence, that average minus the expected value of these random variables will have an absolute value that is greater than or equal to epsilon with 0 probability. So even if you choose the smallest possible epsilon, it says, even if you chose the smallest possible epsilon, it says, after some point, when you increase the number of random variables from that sequence, their average is going to get even more closer to the location parameter, I'm sorry, the expected value mu, okay? So even if you choose the smallest possible epsilon, when you increase the number of random variables in that sequence to be accounted in that average is going to be even more closer to the expected value of these values, okay? So the weak law of large numbers states that. So let's read the statement. The probability of the mean of independent and identically distributed random variables to deviate from their expected value more than epsilon units converges to 0 if the number of random variables is large enough when the average is calculated. And no matter how small epsilon is chosen, after some n value here, after some certain n value here, that convergence is going to occur. And basically, it says that at some point, when you increase the random variables in that summation, or in that average, when you increase the numbers, at some point, that value is going to be even more closer, closer to the mu, even more than that epsilon value that you have chosen, no matter how small epsilon that you choose. So basically, in other words, the weak law of large numbers is going to indicate the strong law of large numbers, which I'm going to tell you later. It basically says that if you take the average of random numbers coming from a distribution with expected value mu, as the numbers in that average increases to infinity, as you use more and more random variables in that average, then their average is going to converge to mu. Okay, so the weak law of large numbers states that probability, but the strong law of large numbers states something much more powerful. Sorry. And basically, the strong law of large numbers will tell you that that average is going to converge to the expected value of these random variables. Now, let's prove the weak law of large numbers. Okay, let's prove that weak law of large numbers. Now, how can you prove that? I think we can use the Chebyshev's inequality, because that probability statement inside the limit, it totally looks like the probability statement in the Chebyshev's inequality if you check that around. Okay, so that probability statement here and that probability statement here, they look alike. Okay, so we have greater than, and we have an absolute value, and we have a difference from the mean, so on and so forth. Now, the only thing that is random here is that average. So the average of n random variables. So let's calculate the theoretical expected value and the theoretical variance of that average, because in Chebyshev's inequality, in order to use the Chebyshev's inequality, we need to know the expected value and the variance of that random variable, right? And the random component there in the weak law of large numbers is an average of n random variables. The expected value of n random variables, average of the n random variables, is equal to what? So we can take 1 over n as a constant multiplier outside the expectation. Then in the numerator, we will observe an expected value of the sum of random variables, which is going to be equal to the sum of expectations. And we know that each of these random variables in the sequence has the expectation mu. So if you sum n expectations, that is going to be n mu divided by n, and that is going to be mu. I mean, if all of these random variables has the expectation mu, then their average is also going to have the expected value of mu. I mean, what would that be, right? I mean, if all of them has the expectation mu, then the average is supposed to have the same expectation. I mean, there is no mathematical explanation for such a actually easy statement to understand, right? However, I mean, this is just a mathematical way of showing that. And now let's talk about the variance. What is the variance of the average of n random variables? All of these random variables are identical with expected value of mu and variance of sigma square, if you remember. Now we have 1 over n as a common multiplier, and that 1 over n gets out of the variance as squared, if you remember. So that is going to be 1 over n squared times variance of the sum. And since xi are independent, remember now my sequence consists of independent random variables, the variance of the sum will be equal to the sum of the variances. And each random variable in this sequence has the variance of sigma square. If I sum up n sigma square, that is going to be n times sigma square divided by n square. And one of the n's in the denominator will cancel out with the 1 in the numerator. That is going to give us a sigma square over n. Okay? So you see, if we have a sequence of random variables which are independent and identically distributed with expected value mu and variance of sigma square, then their average will have the expected value mu and variance of sigma square over n. Now, we know the expected value of this random component. We also know its variance. According to the Chebyshev's inequality, the probability of the absolute value of this random component to deviate from its mean. Now remember, this component has the expected value mu as well. Okay, so this mu here is the expected value of this random component as well. So the probability of the absolute value of this random component to deviate from its mean more than or equal to epsilon amounts should be less than or equal to the variance of that component divided by epsilon square, right? And what is the variance of that component? We have just calculated sigma square over n. So we write the sigma square over n here according to the Chebyshev's inequality, and that is going to be sigma square over n times epsilon square. Now I know that this probability is less than or equal to sigma square over n times epsilon square. What I need to do is this. I am just going to take the limit of the both sides. Okay, so if this probability is always less than or equal to that value, that probability will also be less than or equal to that value in the limit when you take this n to the infinity. And when you take this n to the infinity, that is going to be the left-hand side of the Chebyshev's weak law of large numbers. And when you take the limit of the right-hand side as n goes to infinity, because n is in the denominator, it will converge to 0, which means that probability is going to converge to 0 if you increase the number of random variables that you take in the account in the sum. Okay? And the weak law of large numbers is proven because of that reason. Basically, as n goes to infinity, the probability of the average of a independent and identically distributed random variable sequence to deviate from their expected values to be greater than or equal to epsilon is going to be 0, no matter how small you choose the epsilon. So the convergence will definitely occur. That average in the infinity, if you increase your sequence size, that average will definitely converge to the true average. Okay, definitely.